The moon has always been more than just a silent neighbour in the night sky. It's a constant companion, its bright face familiar to every generation that has ever lived on Earth. But beneath that beauty lies mystery. For decades, scientists have asked one question that could change everything. Does the moon hold water? The answer might shape the future of exploration, settlement, and even travel beyond our solar system. Today, let's retrace humanity's search for this hidden treasure, from the first hints in lunar soil to the exciting missions of today. By the end, you'll see why something as ordinary as water may be the most extraordinary resource in space. Our story begins in 1976 when the Soviet Union launched Lunar 24. This robotic probe drilled nearly 2 meters into the lunar surface and brought back 170 grams of precious soil. Inside the sample, scientists noticed something unexpected: traces of water. About 0.1% of the material contained it, and intriguingly the concentration seemed to increase with depth, but many dismissed it as contamination from Earth. The question of lunar water remained unanswered. 2 decades later, NASA's Clementine mission turned its cameras toward the moon. In 1994, Clementine revealed something remarkable: vast craters at the lunar poles that had not seen sunlight in billions of years. Could frozen ice hide in these eternal shadows, shielded from the sun's destructive rays? The idea electrified the scientific community. To pursue the mystery, NASA launched Lunar Prospector in 1998. Its instruments detected large amounts of hydrogen at the moon's poles, suggesting the possibility of 10 to 300 million tons of water ice hidden within those dark craters. Yet hydrogen does not guarantee water. It could just as easily be hydroxyl, a close chemical relative. Hoping to settle the debate, scientists crashed Lunar Prospector into a polar crater, expecting to see a plume of water vapor rise into the sunlight. But Earth-based telescopes found nothing. The mystery deepened. In 2007, Japan's Kaguya spacecraft entered orbit. While its main mission was mapping, scientists also hoped it might find water. 18 months later, Kaguya 2 ended its mission by crashing into the moon. Again, no clear evidence was detected. For decades, every attempt seemed to promise more questions than answers. Imagine the frustration. Each mission hinted at something extraordinary, yet none could prove it. We were left chasing shadows, waiting for a breakthrough. That breakthrough came from an unexpected source: India. In 2008, the Indian Space Research Organisation launched Chandrayaan-1, its first mission to the moon. Unlike earlier attempts, Chandrayaan carried an impactor probe designed to search for water directly. As the probe descended toward the lunar south pole, it analysed the thin atmosphere above the surface. Within its data, scientists found the long-sought signal water vapour. For the first time in history, there was clear confirmation that the moon does indeed hold water, but Chandrayaan-1's success didn't stop there. Aboard the spacecraft was NASA's Moon Mineralogy Mapper, which used spectroscopy from orbit to detect water molecules spread across the lunar surface. Suddenly, what had been a matter of speculation for decades became undeniable fact. This was the turning point. After years of uncertainty and disappointment, the scientific community finally had proof. We were no longer asking if the moon had water. We were asking how much, where it was, and what it meant for the future of space exploration. NASA quickly followed up with one of its most creative missions. LCROSS launched in 2009 alongside the Lunar Reconnaissance Orbiter, or LRO. LCROSS had a simple but clever plan. Instead of relying on Earth-based telescopes to catch faint plumes, the spacecraft would create its own impact and fly directly through the debris to analyse it. The mission worked brilliantly. The first stage of its rocket was released to crash into a permanently shadowed crater. Moments later, LCROSS itself plunged into the plume of debris, collecting data until it too met its end on the lunar surface. The results were groundbreaking hydrogen, ammonia, methane, and most importantly, crystals of water ice. At last the debate was settled. The moon held real usable water. But discoveries didn't end there. In 2020, NASA's airborne observatory SOFIA detected water on the sunlit surface of the moon, specifically in the massive Clavius crater. The amounts were tiny, between 100 and 400 parts per million, far less than Earth's driest deserts. To put that in perspective, the Sahara has about 100 times more. Yet the finding raised new questions. How could water exist in such a hostile environment, exposed to sunlight and lacking an atmosphere? The answer wasn't clear, but the implication was stunning. Water on the moon wasn't confined to its coldest, darkest corners. It might be more widespread than anyone had imagined. So how does water appear and persist in such an airless world? Scientists have proposed several possibilities. Micrometeorites constantly raining down on the lunar surface may deliver tiny amounts of water with every impact. Another idea involves the solar wind. Streams of charged particles from the sun could implant hydrogen into lunar soil, where it reacts with oxygen-bearing minerals to form hydroxyl. Then, through further impacts, that hydroxyl could transform into water. Once formed, the water might become trapped within glassy beads created by high heat during meteorite strikes, or it could settle between grains of soil sheltered from the sun. Whatever the exact process, one thing is clear: water, scarce as it is, has been part of the moon's story for billions of years. And for us, that changes everything. Water may seem ordinary, but in space it is priceless. It can sustain life-support agriculture and provide drinking water for future lunar settlers. But perhaps its most powerful application is as fuel. By splitting water into hydrogen and oxygen, we can create the same propellants that launch rockets today. Consider the cost of carrying all fuel from Earth. Every kilogram lifted into space requires enormous energy and money. The farther we travel, the more fuel we need, and the more fuel we must carry. It's a vicious cycle that limits exploration. Now imagine mining ice on the moon. With its gravity only 1/6 that of Earth, launching fuel from the lunar surface is dramatically easier. In fact, sending fuel from the moon to low Earth orbit could be cheaper than sending it directly from Earth, despite the extra distance. Lunar water could become the oil of the space age, the resource that makes deep space travel practical and sustainable. The next step is turning discovery into utility. NASA's Prime 1 mission, scheduled for launch, soon aims to drill into the lunar surface near the South Pole and analyse samples directly. The European Space Agency, in partnership with Roscosmos, has planned Prospect, another mission designed to extract and test polar samples. India too is continuing its lunar journey, preparing Chandrayaan-3 as the next step in its exploration. But perhaps the most exciting is NASA's VITA rover, the Volatiles Investigating Polar Exploration rover. Slated to become the first resource mapping rover on another world, VIPA will explore the South Pole, directly seeking out the most accessible water ice. Its mission is not just scientific, but practical, to build the first detailed resource maps of the moon. These maps will guide NASA's Artemis program as it establishes a long-term presence on the lunar surface. For the first time, humanity is not just asking what is out there, but how to use it to go further. The moon is no longer just a destination, it is becoming a gateway. So here we are, after decades of searching, failure and renewed hope. We now know the moon holds water, not in oceans or rivers, but locked in craters, hidden in soil and scattered across its surface. These findings transform the moon from a barren rock into a stepping stone. Water, simple and familiar, could unlock a new era of exploration, allowing us to travel further and stay longer in space than ever before. As we look to the future, let's remember, sometimes the smallest discoveries, molecules of water trapped in dust, can open the largest doors. The moon, once a symbol of mystery, may soon become the foundation of humanity's journey into the cosmos.